Well, hello, ap1. This is going to be Chapter 2, Part 2. We're going to be starting with Section 2.3 on page 230 on a topic called acceleration. We'll use the symbol A with our little vector on top. So acceleration is a vector. So the idea behind acceleration is it is a change in velocity. We're allowed to change our velocity. We can speed up and we can slow down. Thank God for it. I'm sitting in a chair right now, and if I'm going to go to school tomorrow, I am going to have to accelerate. Right now, my velocity is 0, and for me to get to school, at some point, I'm going to need to be going 70 miles an hour on the 215, and I will have to change my velocity to get there. Well, so we have acceleration. Acceleration, oops, I should turn on the pen. Acceleration, we'll just cut to the chase, is defined as a change in velocity over time. In other words, if I'm going to change my velocity, I'm going to speed up or slow down, it doesn't happen instantaneously. It's going to take some amount of time for me to change my velocity. The relationship between that change in velocity and time is called acceleration. Velocity has the units of meters per second. Time has the units of seconds. So acceleration will have the units of meters per second squared. That'll be our preferred units. Okay? Next, we're going to be talking about average acceleration. I'm just going to call acceleration, but I mean average acceleration. We're not going to worry about instantaneous acceleration, but in the context, instantaneous and average have the same basic meaning as they did when we talked about it in regard to velocities. We're just not going to deal with that instantaneous acceleration here. So acceleration is what we'll talk about, and we mean average acceleration. Okay? So an acceleration is a change in velocity related to the amount of time it takes to actually change velocity. Now, acceleration is a vector, and as such, it can be in one dimension. It can be either positive or negative. It can be in the positive direction or the negative direction. It is a very common misunderstanding for people to think that the direction of the acceleration means speeding up or slowing down. Okay? And that is not the case. There is a common misconception that the direction of the acceleration means speeding up or slowing down. That is not the case. I'm going to show you a couple examples to demonstrate that. Before I get to those examples, I just want to throw out there that we do not need to say decelerate. Sometimes in the English language, we say decelerate to mean slowing down. We do not need that. Accelerate means change your velocity. I can change my velocity to speed up. I can change my velocity to slow down. Both of those are accelerating. Okay, back to the sign, the direction of the acceleration vector. The direction of the acceleration vector is not, in general, it does not mean speeding up and slowing down. I'm going to show you some examples now. Let's just take an example where my initial velocity, let's say my initial velocity will just make 2 meters per second, and let's make my final velocity equal to 10 meters per second. Both of those are velocities in the positive direction, and in this case I'm starting at 2 and going up to 10, so in this case I'm speeding up. Let's calculate our acceleration. So acceleration is a change in velocity over time. That means it would be my final velocity minus my initial velocity over time. Let's say for the sake of this that the amount of time is 2 seconds, just to put a number on it. So my acceleration is going to be my final velocity, 10, minus my initial velocity, 2, over my time, 2. So that's going to be 8 divided by 2 gives me 4 meters per second squared. Okay. My acceleration is 4 meters per second squared. In this example, the acceleration is positive, and I'm about to tell you that that is a fluke. Acceleration is positive, but that is not positive because we sped up. Let me show you another example to make this more clear. Let's, in this example, take my initial velocity to be negative 2 meters per second, and my final velocity to be negative 10 meters per second. So this is the exact same idea as before, except this time, instead of traveling in the positive direction, now we're traveling in the negative direction. Instead of going to the right, we are now going to the left. So let's calculate our acceleration. Our acceleration is going to be change in velocity, so v final minus v initial over time. And that's going to be my final velocity, which is negative 10, minus my initial velocity, which is negative 2, divided by 2. That gives me an acceleration of negative 10 minus negative 2 gives me negative 8 over 2 is negative 4 meters per second squared. Well, that's an example of an acceleration that's negative. However, I'm still speeding up. I started off going 2 meters per second to the left, and I finished going 10 meters per second to the left. So I sped up, but this time my acceleration is negative. I sped up with a negative acceleration here, and I sped up with a positive acceleration in this example. So both of those are accelerations that involve speeding up. So clearly, the sign, the direction of my acceleration vector does not mean speed up, right? It means something else. Now this is a bit hard to take, but what it means is, what the acceleration vector means, what the direction means, is the direction my velocity is changing, okay? It means the direction my velocity is changing. Let's do one more example before I finish clobbering you with this one. Let's now say that my initial velocity is 10 meters per second and my final velocity is 2 meters per second, okay? So let's find our acceleration. Again, we're just going to use 2 seconds for our time. So the acceleration is going to be final velocity minus initial velocity over time. So that's going to be my final velocity, which is 2, minus my initial velocity, 10, over time. That gives me an acceleration of negative 4 meters per second squared. Well, there's a negative acceleration, and this time I'm slowing down. The previous example was a negative acceleration with me speeding up. So what does all this show us? Well, this shows us that the acceleration vector is in the direction that the velocity changes. I'll say that another way. The direction of the acceleration vector is the direction that the velocity changes. Let's look. In this case, let's go to this example. In this case, I started off at 2 meters per second. I finished at 10 meters per second. My velocity went from positive 2 to positive 10. My velocity increased in the positive direction. My velocity changed in the positive direction. It got more positive. So my velocity changed in the positive direction, and sure enough, my acceleration was positive. That's the direction the velocity changed. In this example, my velocity started off at negative 2. We finished off at negative 10. I went from 2 in the left going towards the left, and I finished at 10 going to the left. So my velocity got more negative. My velocity went from negative 2 to negative 10. My velocity changed in the negative direction. It got more negative. My velocity changed in the negative direction. My acceleration is in the direction of the change in the velocity. Look at this example. In this example, I started off at 10 meters per second in the positive direction, so to the right. I finished at 2 meters per second, still in the positive direction, so to the right. So my velocity went from 10 down to 2. My velocity got smaller. My velocity got less positive. Another way to say that, my velocity got more negative. My velocity changed in the negative direction. My velocity changed in the negative direction. So the negative is telling me the direction my velocity changed. That's the acceleration. Now, how can I associate acceleration and its direction with speeding up and slowing down? Well, we can say this. If the acceleration, I don't like the way that looked, if the acceleration and the velocity are in the same direction, and remember that could be positive or negative. If both of them are the same direction, in other words, if both of them are positive or both of them are negative, that means speed up. If, the opposite case, if the acceleration and the velocity are in opposite directions, in other words, one is positive and the other is negative, they're in opposite directions, that means slow down. Let's go back to our examples. In this example, we're speeding up. Velocity's positive, my acceleration's positive, velocities are positive, we're speeding up, acceleration's positive, these are positive, acceleration's positive. That was an example of speeding up. Both of them are in the same direction. Let's look at this example. My velocities are both negative, my acceleration is negative. This was an example of speeding up. Velocity and acceleration are both in the same direction. That means speeding up. It just happens to be speeding up to the left as opposed to speeding up to the right. Let's look at this example. My velocities are both positive, my acceleration is negative. My velocities are in the opposite direction from my acceleration. The fact that they're opposite gives me the example of slowing down. In this case, I was certainly slowing down. I really hope that makes some sort of sense, but I'm not going to say it anymore because there comes a point where you can say it too many times. If the acceleration and velocity are in the same direction, then I'm not saying it anymore. Although I'm not saying it again, I'm going to show it to you again. This means slow down. Okay, we're almost done. I just want to go through one more graph. This time I want to show you a velocity time graph. Last graph we looked at was a position time graph. Now we're going to look at velocity time graph. So let's just say we have velocity and time, and we do this. I'm going to go through the same argument I did before. I'll speed it up really quick. The slope of this line is going to be rise over run, right? It's going to be the rise over the run. The rise over the run. Well, the rise is going to be a change in that variable. The run is going to be a change in that variable. So rise over run is going to be change in velocity over time. Well, I'm certainly hoping at this point that you recognize that as being acceleration. So acceleration is the slope of a velocity time graph. Cool? All right. One other thing that this is going to be a tiny bit of calculus for you. I'll draw another graph just so we don't mess up that one. Something else that's really neat. Your book doesn't go into this, but this is just going to be an added extra for you. Let's just say I have velocity like that, okay? And let's just imagine there. So there's my line, and I just drew a vertical line there to emphasize a point. If I look at the area underneath my line, so I look at that area, right? That is the area, that shape happens to be a triangle. The equation for a triangle is 1/2 base times height. 1/2 base times height. Okay? What units will that have? Well, the base is this, so that's going to have units of seconds. The height is this, that's going to have units of meters per second. So meters per second. So if we have meters per second, if we have seconds and meters per second and multiply them together, what will we get? Well, meters per second times second gives us the units of meters. So the area underneath the curve on a velocity time graph, the area underneath it has the units of meters. Well, guess what? So does that. That also has the units of meters. That means the area under a velocity time graph is displacement. This is so cool. A velocity time graph tells us everything we know so far. I can read off a value from right here. That tells me the velocity. I can read off a value this way, and that tells me the time. I can measure the slope, and that tells me my acceleration. I can measure the area underneath the slope. I can measure the area under here, and that tells me the displacement. For those of you that get to calculus, that's going to be called integration someday, but don't worry about that for now. Okay, I think that wraps up everything we need to talk about for this video, so I'm going to call it here, and we'll start working